Learning with eyes.
To eyes education, the only education that matters. The on the previous video on YouTube, if you remember, I've shown you how to get the equation of the motion of a system of multiple degrees using Lagrange. So basically, that part emphasized more about part one. Okay, I just wanted to show you how this look. This is the integrality of equation that you should expect during your test under this chapter. You have two type of questions. You have this one, and you have the other one where you have to declare for the steady step and also, but we'll see all of them. But this is the first one. You can see how they look. It is 6, 4, I think it's up to 20 marks, one question. So it all starts with equation of the motion using Lagrange's, which I have shared 2 examples on my YouTube channel. So when I said that I don't know where to start here, I was asking because for some it is the first class joining, so I don't want to start from there because I wanted to take one of the equation where we solve for 1.1 and solve the rest. But because I can see some new faces around, I can always restart here. We can solve this system here together using all these steps here. If we can finish all of them, we finish them. Then the next time we continue. So yeah, that's what we'll be doing right now. Okay, yeah. Okay, guys, if you remember last time I said in theory of machine we used to call it single degree of freedom. You only had one object doing whatever motions. Or in theory of machine, you guys used to have something like this. Let's say you have it's just, how do we call it again? I think it's a spring, something like this, swinging either up or down. So we used to call this one a single degree of freedom. So literally, you can see that you have two objects attached to each other through a spring. So because of that, and another thing that I said, how do you know that you have multiple degrees of freedom? You can just identify the number of masses that you have on your system. Like for instance here, this system here, I have one mass B and one mass D here. Because I have two masses, I can already see this is a multiple degree of freedoms. So I'll be having two movements. I used to have something like this. Let's say it is a spring going up and down, and from here we're asked to solve for the equation of the motion, and we're asked to solve for natural frequency and so on. You can even see here it is the same, but you will notice here in this case the approach will be different because this one is a multiple degree of freedom. So I wanted to ask, when you look at this system, how is it moving? Is it moving linear or is it moving angular? A quick recap is, when you have a linear movement, it's either you are moving up, down or up, or you are moving left or right. What do I mean by that? If I have a car, this is the car. Yeah, don't mind my drawing. This is how we used to draw a car in primary. This car will have a linear motion because it will be moving on the road. Let's say either is moving like this or this way. If I have, let's say, a pendulum attached to a spring, I can only expect two movements. It's either it's going to be down or up. There, I can say it is linear. But if you look at the pendulum, let's say something like this, attached like this, and it has moved through a certain angle. Because of the angle created, we say that the movement is angular because it is creating an angle. It is swinging through an angle. I don't know if I'm making sense. So far, when you look at this system, can you tell me, is it angular or linear? Because you have to be able to identify it. But for you too. Talk to me, please.
That's linear.
No, this cannot be linear, my friend.
It's angular. It's angular because of that pivot there.
Because you see the pivot point, this thing can only swing. It can only, if it was here initially, it can only swing and create an angle. Same apply also here. Because the angle is created like I was explaining here, therefore you have an angular motion. It is very, very important to know. Why am I insisting on angular and linear? Here is the reason why. Let me write it down. Hey, Mr. Cabello, how's it, my brother?
Good, thanks. How are you, man?
I'm glad to have you, my friend. If you have a linear motion, what is the kinetic energy of a linear motion? Kinetic energy of a linear motion is simply T is equal to half mass of the object linear velocity square. If you have a angular, kinetic energy is simply half moment of inertia of that object multiplied by angular speed square. So it is very, very important to identify which one are you dealing with. That's the first step. So far we know all this thing is angular. Now what is the next step? I identify my number of masses. How many masses do I have? Number of masses gives me number of moment of inertia that I will need in this problem. Now in this problem here I have two masses. Remember Lagrange's, when we talk about Lagrange's, all we need is kinetic energy, potential. If we have a damper, we have what we are the relay dissipation. But another thing, you will never have a case with a damper with this question aligned here. There is a reason for that, because they are not applicable when you have a damper. So most of the time when we be answering this question, there will be cases where we do not have a damper. Now, let me just let me get my note quickly. Mr. Capello, let me not make the same mistake as last time. Let me plug my Wi-Fi. Yeah, I think it's charging now. So this is where we are. So in Lagrange's, what we need to call what is called potential in kinetic energy and potential energy, and also relay dissipation in case of if it's needed. I said relay dissipation comes from the damper. So what do we need to know? I just need to recall the formula of the Laplace. How do we write? What is that formula again? The formula says if you have d in term of time, partial t over partial qi minus rho t rho qi plus rho u rho qi plus rho r. If you have not watched the video on YouTube, please watch it. It should help you to understand this further. So now what's happening here, guys? We have to be able to call kinetic energy and potential energy. So in this case, we know that the system is angular. So we can come here and write kinetic energy will be made of the first masses and also of the second masses. So it will be, I will call the first, what is the first, if it's a pendulum, I'm not sure. The first pendulum here, I will call it 1. The second one, I will call it 2, just to make the difference. So basically, kinetic energy will be made of half I will call this one J1 theta 1 dot square plus half J2 theta dot square. I just called it like this to make the difference between this guy. So the next thing is potential energy. What is potential energy? Remember, potential energy, U is equal to half K and the displacement X. What displacement are they talking about? I'll explain just now. So in this case, let me explain what I mean by displacement. This pendulum was initially here. As this thing is moving, let's say this way, the spring will oppose. sorry. As it's moving, it creates we call it arc length in mathematics. It creates a arc length, a angular displacement. If you remember well from, let me just take a random example from mathematics 1. When you were doing when you have a circle, let's say this is the center, from here to here is the radius. Let's say this thing has moved until here. This also a radius. It creates a distance. The distance from here to the second point is what we call arc length. So in this case here, it is our displacement x due to the angular motion created. Same apply here. It was initially here. Now, as it is moved, it is now here. So there is an arc length created. The arc length is simply the displacement at which we are talking about here. Now, what is the formula of arc length? If you remember well from Met 1, we used to say that arc length is equal to r theta, where r is the radius of the circle, theta is the angle created. So if we can refer this to what we have here, in this case, what will be our r? Our r will be the distance from this guy to here. I don't know if you see it, which is 0,3 plus 0,3. Let's call this distance L. Let's just forget about values for now. Let's say the distance from the pivot to inside here, because that's why it's ending here, is L, 0,3. Let me erase this one, because if I do this, this becomes something else. So L is from the pivot to where the center of gravity of the mass is. That is our L. So in this case, our displacement x is simply going to be L theta. Any question, guys? Please speak to me. Any question? Are you with me?
Yes, you can continue.
Okay, thank you, my brother. What is next? What is next, Mr. Cabero? Now that we have this one, we know that x is equal to L theta. Let's apply it in our formula here if we are together. It is really, really important. Very. Yes?
Are you not going to have an equation for the potential energy of the second mass?
Yeah, I wanted to write everything now. I was just explaining what's happening.
Okay. All right. Yeah, that was the question. Yes.
Okay, any other question?
No, I don't have any.
Oh, yeah. Okay.
Okay.
I appreciate it, yeah. Now, my guys, what do we do? If you do remember, last time, what did I say when we came? If we have a spring attached to two elements, what did I say? It means we have a change of displacement. Let's say for you here, I will say, I'll write half, right? I'll have K, and what will I have here? because this spring is between this element and this element, there will be a change of displacement. Are you guys with me?
Okay.
Because the spring is attached to this guy, is also attached to this guy, so there will be a change of displacement. So let me say it doesn't matter if you go final minus initial, but to keep the consistency, I think I've been going final minus initial. Remember, sorry, this formula has a square here, sorry. Now, so what's happening here? Let me write x theta 2 square. When I'm writing x theta 2, I'm just showing you that it is the displacement created by the angle theta 2. I hope I'm making sense. Or let me not think much. Since I call the other one 1 and 2, let me keep consistency. Let me say x2 minus x1 square. The only reason why we do have this change is because our spring is attached to two elements. I do believe that we all together, right, guys? You can check my previous example on my YouTube channel. There is this there that was posted there. Have you checked it, Mr. Cabello? Okay, now
Yes,
to
I
make
have.
the difference here, let's say we have x2. X2 will be L theta 2. Remember, this is what I was trying to explain here. X1 will be L theta 1. So we're gonna take it and substitute to the formula here. So definitely our u will be half k multiplied by L theta 2. Let me put it like this to make the difference. Everything here is square minus L theta 1. Everything here is square. Let me check my video on the phone just to see, because I think on the last video I have done something like this in the second question. Thank you for the subscriber. I see someone subscribed. I guess it's one of you. Mr. Cabello? Any question? Are you with me? What can... Yeah. Who's joining now? Sorry, let me just add this person. Guys, please take the videos when I post it. It will make our life easier. I know that you guys are busy. You are chasing the bag. But from time to time, get the time to check the videos. There's something I wanted to confirm. Yeah, I think. No, it's fine. Yeah, you with me?
Yes, I am, As.
Yeah, sorry about this. Let me do this.
No problem.
Yeah, sorry. I just confirmed. In fact, I watched my video to prepare my own class. So do the same. I watched my previous video to come to class. Sorry. This is how the displacement will be. So it's going to be K. So in this case here, inside we'll be having L theta 2 square. No. I'm repeating the same mistake. Minus L theta 1 everything square. So I believe that now we're good. From now we can start calling our equation and solve the question. Now guys, once you can call your kinetic energy right, your potential energy right, there is no way we can fail such equation. Now let's look at it. What do? I'm gonna try to move a bit fast so that we can be able to solve couples of these questions here today. Now, here we go. We have to go for Qi, if we can say for Qi to be theta 1. Let's apply the formula. The formula say it is rho t. So we're gonna go rho t, rho, what is Qi? Qi is theta 1. This one is dot, eh? So it's going to be theta 1 dot. So what is the differentiation of kinetic energy in terms of theta 1? So basically what we are doing what we call partial derivative. I hope you are with me. So in this function on top here, if we differentiate in terms of theta 1, what are we going to have? We know already that because theta 2 is not part of the variables, therefore it's a constant. So our main focus is this guy. So if we differentiate this, what we will be having is the half will be here, the 2 will drop, so what will be remaining will be J1 theta 1 dot. So at the end of the day, the answer is J1 theta 1. I hope we are good with this one, guys. I hope we are good with that. Yeah.
Yes, we are good. Yes.
So, my brothers. Now, in this case, when we differentiate, then when we say, if you look at the formula says you differentiate in terms of time. This expression. So first, you get this expression. Second, you differentiating in terms of time. So basically, you are differentiating in terms of time the expression J1 theta dot 1. Because the variable is time, the velocity will move to acceleration. That's why here we'll be having J1 theta 1 dot dot. So we are done with this guy here. We move to the second expression. What is this one? And I say that one will always be 0. We just write the formula because we have to write it. What is the reason? Because if I take partial t, partial theta 1, if I want to differentiate in terms of theta 1, remember my variable are all theta dot. So we don't have any variable in the kinetic energy that has theta 1 on its own. That's the reason why the second expression will always be 0. We go with that, right? Now we move to the third one, rho u, rho q1, where in this case q1 will be theta 1. It's quite fast. It's not that complicated. Rho u, rho theta 1. Sorry, why am I losing my voice? Now, in this case here, remember here we have what we call chain rule. Whenever you have something with a power that you have to differentiate, we have what we call chain rule. I think I explained it last time. Let me just recall it. The formula says if I have u to the power n, I will have n u prime u n minus 1. I will explain now.
Mr. Ice.
I will write now. I will rewrite. That was the concern, my brother.
No, on the first partial derivative.
Yes, boss.
We also have J2, most. So are we doing them separate or?
Yeah, remember in this case we said the formula says it is Qi, right? On the Qi you have two variables. You have variable with theta 1 and variable with theta 2. That's why I said for Q1 to be theta 1. So in that case, it means we'll be doing everything partially where the variable is theta 1.
All right.
Did I answer you, my boss?
Yeah, thank you.
You're welcome, brother. Now, u prime, u n minus 1. Let's do this thing here. Let's forget about the half k. let's just do it for explanation. We have L theta 2 minus L theta 1 square. So we can already see which one is our U, is the guy inside here, everything. Let's apply the formula. The formula say it is N. N is 2. So we drop 2. They said U prime. U prime, we differentiate what is inside. I feel like my pace is too much. Am I going fast, guys? Hello?
You're fine.
Okay, now
You're fine. Can I please ask a question?
Yes, boss.
This first equation is for the next B, no?
Okay, yeah, I called B to be 1 and I called D to be 2.
Oh.
Yeah, I just called, you can write MB, MD, but I just called M1, M2. Yes, it's B, Mr. Cabello,
okay.
if it's understandable that way. Yeah, my boss, please, let's move. U prime, you differentiate what is inside. Because the variable is theta 1. Because the variable is theta 1. Theta 2 will be a constant. We are differentiating partially in terms of theta 1. Whoever which is not, theta 1 is a constant. So this whole expression here will be 0. That's why U prime, if you differentiate in terms of theta 1, you're only gonna have minus L. Basically, let's say you have minus 2x. What is this differentiation? It will only be minus 2. So in this case, it's gonna be minus L. Now, they said U, what is U? U is everything as it was. L theta 2 minus L theta 1. They said U, everything n minus 1. Remember, n is 2, n minus 1 is 1. So if we have to, we can make everything easier here. We can take L as common factor and take the minus here. Let's say minus 2. It's going to be 2L square. Inside, we can go theta 2 minus theta 1. And again, yeah. Any question, guys, with this differentiation? We just used what we call chain rule from mathematics 1, I guess. 1. So let's apply it. Let's apply it. You see how it's gonna go. So basically, we'll have partial U over partial theta 1. So remember, we had the half k in front. This is the differentiation, which is minus 2 like this, L square like this, multiplied by theta 2 minus theta 1. So you will notice here 2 will cancel out 2. So eventually what we'll be having down here will be k L square multiplied by theta 2 minus theta 1. Again, you can expand it. So you'll have k L square theta 2 minus k L square theta 1. So what you have here, guys, we basically solved for the potential energy of theta 1. So how do we rewrite the equation? Again, if we follow a general formula, we say that plus rho r over rho qi to be equal to 0. In this instance here, this will be 0. We have relay dissipation if we have a presence of a damper in the system. So if there is no damper, it means this part will not exist. So basically, we have solved for everything that is needed in this equation, and we have to equate it to 0. So what do we have to do? We simply have to copy now. You just copy. What is the first answer that we get? It is j theta 1 dot dot. So equation 1 will be j1 theta 1 dot dot. What is the second answer that we have? It is this one. Let me just recall like this. Let me write minus k L square theta 1 plus k L square theta 2 to be equal to 0. So this is how you get your first equation. So we do the same for the second equation. Are you with me, guys? Hello? Yeah. Please talk to me. I cannot see what is on the other side because I can only see my screen. So I don't know if you guys can hear me or everything is going smoothly.
Okay. Yeah. Minus K L2.
Yes, you can ask the question, my brother. You can.
Yes.
My dear, you open the mic. Do you have a question? Okay, yeah. Now let's go for QI, which is theta 2. Same apply. We will go rho theta dot of 2. So now what do? We scroll up to the formula sheet. We check. Where do we have theta dot 2? Is this one. So this guy here is a constant. So we don't have to even worry about it. It will be 0. Now, how do we do it? We're still gonna have half. Now, half J. Now, what is happening is you drop the 2. How did I write here? Let me keep the consistency. Yes, let me keep the consistency. Half here we drop the 2. We still have J2 theta dot 2. So 2 will cancel 2. So the answer is J theta dot 2. So now we differentiate in terms of time. Sorry, this is J2. Ne? J2 theta dot 2. The answer will be J2 theta dot dot. As easy as it is. I have a question that I wanted to ask before I even proceed here, guys. I have a question that's popped in my mind. I said J is a moment of inertia. How do we solve for moment of inertia, Mr. Cabello? In this case, I will continue with that equation. I just had the question to ask you. How do we solve? Let's say we want to solve for J1. How do we solve for this moment of inertia, guys? Yeah. Hello? Hello, guys. Can you hear me? Yeah.
Yeah, we can hear you.
Then
Sean, okay. How do we solve moment of inertia in this case, guys? Because this is J. Let's say you're asked to solve for this. Okay. If you don't remember, do you guys remember what we talked about concentrated mass, guys? This is another topic as well. But since it just popped in my mind, let me just take like 2 minutes to explain what is here. Okay, yeah. This object is a mass. A mass usually, if they did not specify a shape of the object. Remember from theory of machine, when we used to solve moment of inertia, we need to know the nature of the object. If it is a disk, if it is a sphere, or if it is whatever object it may be. We talked about concentrated mass when we have a shapeless object. By shapeless, I mean an object that we cannot describe by what we know. Let's say disk or sphere, etc. In this case, because in the problem here, I'm not sure if they say what's the nature of this mass. They even said it, which is nice. They say that AC carry concentrated mass. So whenever you hear the word concentrated mass, it simply means it is a mass of a shape which we did not know. In that instance, if we want to solve for the moment of inertia of the concentrated mass, it is simply the mass of that object. Let's say I'm focusing on this one. Let me call this one M1. So it is simply M1. M1. Now, the distance where the center of gravity of the mass is to the pivot point square. So in this case, it will be M1L square. So that is just when you want to substitute value, because we will need them to solve the rest of the question. I just remember it now. That's why I wanted to recall it. Let's say, guys, these objects here, they were not concentrated mass. What will happen here? Yes, you can ask a question. You don't have to raise your hand. Just ask.
Mr. Alex, please repeat on what you just said there.
Okay, I will repeat, my brother. What I was saying is, let me erase even so that I can recall it. If you heard about concentrated mass, it is simply an object that we cannot describe the shape, because we have moment of inertia of a certain shapes that we know. Let's say, for instance, we've got a sphere. Moment of inertia of a sphere, just a quick reminder, is 2/5 mr square. Moment of inertia of a disk, it is half mr square. But this object is a concentrated mass. You don't know the nature of it, so it does not have a formula to it. That's why we call it concentrated mass. Now, how do you solve for the moment of inertia of the concentrated mass? The formula is simple. It is simply the mass of that object. Let's say it is M1. Now, the distance where the center of gravity of the object is to the pivot point square. So in this case, that distance is what we call L, which is 0,3 plus 0,3. L square. If you do this, now you have solved for the moment of inertia of this object here on M1. You have solved
So
for
I
M1.
if we don't have a pivot, if we do not have a point, does the moment of inertia formula remain the same?
No, here is the thing here. You can ever have a moment of inertia without a pivot point.
I can never.
You cannot have moment of inertia without a pivot point.
Okay.
What is the reason,
Okay.
Yaya? The reason is
I think the
simple.
mass.
No, say your mind. Maybe you can have a point.
No,
You say?
please explain it.
Oh,
Maybe my
no,
explanation
I was
is
saying, Yaya,
best.
remember, in the beginning, I took time to explain the difference between these two. The only reason why there's a difference between these two, if you have an angular motion, you will always need a reference point. It
Okay.
is always there, because you cannot just turn around you.
Okay. I
Yeah.
get you. All right. Thank
So
you.
that's why you will always have a pivot point when it comes to an angular motion.
Okay.
Did I answer you? Yeah.
Yes, you did, Ice. Thank you.
No, you're welcome. Let me just check the time if I can resend a new link. 10
Yes.
minutes is a lot, Mr. Capello. A lot can happen in 10 minutes. So that was just it. Sorry, I don't know if I ran out, but out of the concept. I don't think it's that. But this just popped in my mind to remind you how to get moment of inertia. But I will explain further as we move, because I will remind you also of what we call parallel theorem on moment of inertia. I will explain it. It's very, very important. Very, very, very important. Yeah. Now, let's do the same thing here. We are back here. What will be next? Next year, we'll have partial theta 2, which will always be 0 as well. I don't even know why we write it. But remember, this thing is a game. You do one, you good. You do one, so you get it. It's very easy, Mr. Cabello. Now, let's solve for rho u, rho theta 2. Again, we'll have what we call chain rule. But let's do it once off. instead of side by side. Let's say we have half k. Now let's apply let's apply, how do we call it? Let's apply the chain rule on where the variable is k2. Remember, let me just recall that thing. I think it was half k. We open L theta 2 minus L theta 1 square. Let's do this straightforward here. So it is half k. The 2 will drop according to the formula. We differentiate what is inside, but now the variable is theta 2. So it means this guy will be 0. So if we differentiate what is inside, what are we going to have? We're simply going to have L. Remember, only the L will come out. And then we copy the U, which is L theta 2 minus L theta 1, n minus 1, which is 1. So 2 will cancel 2, So what we'll be having here will simply be k. If you know, I can take L outside. I'll have KL square theta 2 minus theta 1. Now if we expand again, we have KL square theta 2 minus KL square theta 1. Like I said, it is a game. It is very, very easy. Now we can recall this to write equation 2. So which is going to be J2 theta dot dot 2 plus KL square theta 2 minus KL square theta 1 to be equal to 0. Any question, guys? Now we can write them in matrix form. Very, very important. Always write your answer in matrix form. I think let's write it in matrix form and then we send a new link to answer the other parts. Equation 1, equation 2, like I said, I always like to recall it so that when I write my equation, I know what I'm writing. So it is J1 theta 1 dot dot minus K L square theta 1 plus K L square theta 2 to be equal to 0. So on this guy we have J2 theta dot dot 2 plus KL square theta 2 minus KL square theta 1 to be equal to 0. So we have equation 1 on top, equation 2 at the bottom. Let's write it in terms of matrix form. If you do remember, I said the first matrix has to go with theta, what is that? With theta 1 dot dot and theta 2 dot dot plus the second matrix expression has to go with theta 1 and the second one with theta 2. Everything to be equal to matrix of 0 and 0. Now, how do we fill the matrix? It is very easy here. Remember, like I explained last time, theta 1 multiply what is here, theta 2 multiply what is here. So basically what we do is what? We look at theta dot 1 1. Do we have it in expression of 1? Yes. Do we have it in expression of 1? Yes. Because of that, what is next to it? J1. We can write J1. Now, theta 2. Do we have it in the expression of 1 here? We don't have it. Because we don't have it, this should be 0. We come on the second one. Okay, theta 1. Do we have it in the expression of 2? There is no theta dot dot 1. So this side should be 0. Now, theta dot dot 2. Do we have it in the expression of 2? Yes, we do have it. Because of that, this should be J2. Now remember, guys, this diagonal should always be the same when you do this equation. If you get them different, it means you are making a mistake somewhere. Again, I think we are left with 2 minutes. Just want to finish this and send a new link. Now, let's do this. we are here. We want to place this k here. Now, theta 1. Do we have theta 1 on the first equation? Yes. What is the expression? The expression is minus KL square. Now,
in simple terms, you're taking the coefficient, né?
Yeah, I'm just taking the coefficient
No.
next to it. Now, do we have theta 2 on the first one? Yes, we have it. It is KL square. Because we have it, this side here, we need to have the KL square. Now you come to the second equation. You check. On the second equation, do you have a theta 1? Yes. What is the coefficient next to it? The coefficient next to it is what? It is minus KL square.
Diagonally here,
You say
the signs same.
The signs are not the same.
I don't
Then we
know.
made a mistake here.
Yeah.
Then that's the way to check we made a mistake. Because this one will be minus KL square. Do we have theta 2? Yes, which is KL square. Now, this actually tells us that we made a mistake. So now we have to go up and recall what is the mistake. See this first derivative here.
Yes.
On the first derivative, guys, what do we have? If you look, we said we have minus 2, right? Cancel. I forgot the minus here.
And I did remember to remind you, but I also see what was gonna happen if we forgot the minus.
But at least you see what I was saying, that because when I'm solving my problem, I see something is not matching, like I'm not having what I need to have. I know I made a mistake. So somehow I'm glad that the mistake happened.
No, but I think you ended up including the negative, yes.
Because remember, the negative is still here, guys. When we multiply, negative times this will give negative KL square 2. Negative times give will give positive KL1 square. So this one should be positive and the other one should be negative. So this changes everything, Mr. Cabello. So let's recheck equation 1. Let's change positive and the other one negative. Good, yeah. So now let's look at our matrix now. If they are symmetric, definitely we do know that answer is right. Okay, here we go. Let's do it again. We come to expression 1. Do we have a theta 1? Yes, it is KL square. On expression 1 here, do we have a theta 2? Yes, it is minus KL square. Now we come here on expression 2. Do we have theta 1? Yes, it is minus KL square. And on expression 2, do we have theta 2, which is KL square? Because these diagonal are the same, I can confidently agree that this equation is right. Now, if you look at the question paper,
Mr. Ice.
Yes, boss.
Please just repeat how you feel. How you feel in those.
Yeah, you are right, my brother. Because even myself, I'm not
It's
convinced
supposed to
that
be
I'm feeling it.
vertically.
Okay, my brother. If I can just try to make it in the easiest way, right, my brother? All the expression of theta 1 will be in this row.
That
This one.
it doesn't work.
Yeah, it doesn't
horizontally.
Work. All the expression of theta 2 will be on this row.
Okay.
Now let me recall how am I doing that, my brother. I know that here I should fill theta 1, right, my brother?
Yes.
What I do is I come to the expression 1. I know expression 1 is where I have theta 1.
Yes.
I said, okay, on expression 1, do I have any expression with theta 1? Which is this one?
Yes.
I copy, I paste.
Yes.
I check again. On expression 1, do I have an expression with theta 2? Yes, which is this one. So basically what I wanted to say is all the expression of theta 1 lies on this row. Like this.
Okay.
They follow. Theta 1 is this row. Theta 2 is this row.
Oh, because I thought if the notation is written theta 1 at the top and theta 2 at the bottom, then that's how in the matrix it must be.
Wait, let me write what you are saying because I need to clarify.
For instance, do you see? Yeah, you see that matrix? It has theta 1 at the top and theta 2 at the bottom.
Theta 1 at the okay, I see, like theta 1 at 2, theta 2 at the bottom.
Yeah, for instance, if the small matrix with theta 1 and theta 2 starts like that, I thought that also in the big one, it will be theta 1 at the top left corner and theta 2 at the bottom left corner.
That logic works as well.
Okay.
Normally what you do is theta 1 multiplied by this, theta 2 multiplied by this.
Okay, no, I get you, sir.
No. By the way, your logic makes sense as well.
Yeah, because now theta 1 is at the top and theta 2 is at the bottom.
I think the way you are thinking is even the easiest way of doing that. Literally, guys, what he's saying is where you have theta 1 expression, you put it on top. Where you have theta 2 expression, you put it down.
You put it at the bottom.
You can also come here and say, where I have theta 1, I put on top. Where I have theta 2, I put on bottom. You still get the same thing. I think, thank you, my brother. You actually gave me another way of doing this. Guys, do you understand this question? Yeah, Mr. Cabello.
No.
Oh, okay. Let me. Okay, literally, it's a matrix, right? What actually happened here? When you multiply out, you need to get what we had here initially. But what we do is we do theta 1 multiply by this expression, theta 2 multiply by this expression, and you go again theta 1 multiply by this expression, theta 2 multiply by this. But now he actually came with a brilliant idea in this case here. It is quite easier. What he's just saying is, because we know theta 1 is on top, theta 2 is at the bottom, what we have to do here is, you can just come, let's say I come to equation 1, right?
Yes.
I look at theta 1. What is the expression that has theta 1? It is KL square. Because I know theta 1 has to be on top, because it is the first equation, KL square should be here. Now again, I can do the same thing with equation 2. All I have to do is to identify where do I have theta 1. Because
it will be negative KL.
Yeah, because I know theta 1 has to be on top, I can confidently copy and write negative KL square. Do you understand now?
I'll stick to your way. I don't think I understand this one.
That other one.
Let's stick to yours, Shem.
Yeah, let's stick to that other one. But then it's okay.
No, but it's fine, Mr. OG. Do you understand
Yes,
that way, ne?
Yes, sir.
Yeah, keep it that way, my boy. If it works, you don't change it. Now, my guys, before we move to the solving, remember, if we got to normalize whatever here, we need to get the values of hey, what's the English killing me? The value of our matrices. So what we're gonna do here, guys, Let's just try to substitute quickly and solve the question. We are given the mass, both masses are 1 kg. We are given the spring to be 500. And we are given the distance to be 0,6. So please help me with the calculator. Let's do this calculation quickly. Yeah. We need to replace value.
Yes,
Remember, we need to replace J1. I have explained there, I say that J1 is simply M1 multiplied by L squared. So in this case, M is 1. The distance is 0,6 square. What is the answer, guys? No, why am I thinking what is the answer is 0,6 square. What is 0,6 square? I think it is 0,006. I'm not sure. Yeah, please check for me.
0.36.
Oh, it's 0.36.
Yes. That's what I'm getting. I don't know if everyone's getting the
That's what
same.
you're getting. That's the answer. Okay, guys, remember also, what am I saying? Remember also here, the masses are the same. They said both masses, they are equal and they have the same length. I don't know if we see. If you look at the problem, let me zoom out a bit here. It is 1 kg, and they're both located at the same distance. So the moment of inertia should be the same. I don't know if you are making sense. Am I making sense, good people?
Yep.
Yes.
Okay, yeah. So definitely, the answer here should be 0,36. 1 minute, yeah. My laptop is on how many percent? 37. Let me just finish this. Why am I not? Damn. Yes, yeah. My charger is here. Hey, Mr. Cabello. It's gonna be difficult. But we'll keep on moving, Mr. Cabello. Left, right. Okay, guys, are you with me? Yeah.
Yes.
How did you get the 0,36?
Okay, my boss, we know that moment of inertia. Let me zoom up a bit. What I was explaining, I think I stopped here, Mr. Oji. I say that because we have a concentrated mass, we know that J should be the mass of this object where the center of gravity is to the pivot point square. So that distance, they say it is 0,6, which we call L square. Now for object 1, they said it is 1 kg. That's why we have 1 times 0,6 square. Now, Mr. KG, if you notice, the mass at 1 is the same as the mass at 2. And they are both at the same distance. So you only have to calculate 1 and repeat it. That's just it, my boss. It's gonna hurt.
Okay, I see it.
Thank you, my brother. Okay, yeah. Can we do the same here, guys? Remember, K is given as 500 kilonewton here, if I'm not mistaken. Oh, 500 Newton. Can you do this calculation? Remember, L is 0.6. So for this one, KL square, it is 500 times 0.6 square. Where am I? There's something that I need to check. Yeah, please give me the answer. What's the answer, guys?
I'm getting 180.
180. So I do believe.
So what's the value for the masses there at the top?
Wait. Let me try to get your question. The mass at the top. You mean what, my boss?
Yeah. What? Yeah. What's given is? Are we given? Oh yeah, it's 1 kilogram each.
Yeah,
Oh, okay.
it's
I
even,
see.
it's stated in the problem even.
Yes. I didn't see it. I see it now.
No stress, my brother. Yeah. Please, guys, go check my video. Like I said, I watch my videos to prepare the classes even. Yes, what's the answer? I'm gonna confirm something here. 180, Mr. Kabilo, what do you get? Yeah, it's good. Yeah, key 180, right? If Yaya gets 180, I believe that you all get 180.
Yes, that's correct.
So this one is minus 180 because it's the same value here. It is the same. You don't have to calculate everything. Okay, yeah. Okay, now the first question they said normalized. We need to normalize K. Normalization K is written like this. So there is a formula for it. Very, very important. The formula of normalizing K is simply equal to M half multiplied by K multiplied by M half. So, guys, why is this video not running? The main important thing here, guys, when you have written this, remember the M and K here, it is simply standing for your matrices written here. So the matrix that you write where you do have this guy here, the acceleration, let me call it like this, it stands for M. The matrix where you do have your springs, it stands for K. So you do have the matrix M and you do have the matrix K. So what is next here? It's simply how to apply and what is half and what is whatever. You will see. I will explain it right now here. Yeah, there is a formula. Let me just write it for you so that you see what we are doing. The formula on the textbook say m of half of minus half. It's simply inverse root what they mean. It is simply a matrix of 1 over the root of m1. This one is 0, 0, and this one will be 1 over the root of m2. So literally here, guys, there is nothing difficult. All you are doing is solving the problem. I mean, applying the formula. So how do we do it here? Here, your m is simply this value, your m1. Your m2 is simply this value. Fortunately enough, in this question, they are the same. So if we have to solve for m of half here, we're going to have 1 divided by the root of 0.36. This is 0, this is 0, over 1 divided by the rule of 0.36. What is the answer here? Mr. Capello, are you still with me?
Yeah, I'm here.
No stress, no stress.
1,6667.
1,6667. Hey, why did this guy call me? Thank you, Yaya. Kalebua. Now, you have already solved for this. Now, what is next? Now you are doing matrix multiplication. This is basically math, guys. It is basically math. So what we'll be doing here, Mr. Cabello, like I said, we have to be able to identify. Let's call K again. We know that K is 180, 0, no, not 0, minus 180. Sorry about my writing there. Minus 180. Oh, what am I writing here? Yeah. So that is K. So now, for instance here, K multiplied by m half. What is the answer for that? Basically, what you are doing is you are doing the matrix multiplication of 180 minus 180 minus 180 and then 180 multiplied by what we have found, which is 1,6667 0 over 0 1,6667. So yeah, what's gonna happen is we will do this multiplication of these two matrices. The answer that we get, we multiply it again by m half. Then after that, we have normalized. It's a bit let's see how it's done. Yeah, how do we solve for a matrix multiplication of 2 by 2? This is where we have to remember our mathematics. Now, what I want you remember at the end we're going to have a matrix multiplication of a 2 by 2. But what is happening here? Yeah. Mr. Cabello.
Do we not do the same thing we were doing with stability?
With what? No, remember this
Do you not calculate it the same way?
No, this one is different. Why? Because that one was a matrix of 2 by 2 multiplied by 1.
Okay.
This one is a 2 by 2 multiplied by 2 by 2. So math should be done. But it's not difficult. Let's do it, yeah. Okay, let's say we want to fill the first row. On the first row, we will have this multiplied by this plus this multiplied by this to make this first row. Basically, we will have 180 multiplied by 1,667 plus, let me say, minus 180 multiplied by 0. That makes the first row. Any question, Yaya?
No questions asked.
Okay. Now let's move. How do we fill the second row, and how do we fill the second row at the bottom? Second row at the bottom. Second row at the bottom. We go this. I don't know. Let me use a different color. You go this one here multiplied by this plus this multiplied by this. What I will do is, after the class, I will take the formula sheet of the matrix 2 by 2 and share. We have 180 multiplied by 1,667 plus 180 multiplied by 0. This makes the other row at the bottom. No. No, yeah. No. Mr. Cabello? No, it's making sense, but it's not the right way of doing it. No. Mr. Cabello, are you with me?
Sure.
Hey, Matrix one is here. No, it's not Nisa ring. I just want to explain the logic behind it. It is not complicated. On the first one here, to fill the first row. Okay, let me just highlight something. I think that can make more sense. If we want to fill the first row here, what we use these two guys. If we want to fill the first row here, what do I mean by that? 180 multiplied by this plus 180 multiplied by 0 makes the first row on top. Now 180 multiplied by 117 here, like this. Now 180 multiplied by this plus this multiplied by this makes the second row here. So if we have to fill the other row here, we make this guy has priority. There's a lot of matrices here, guys. We'll do 1 and 2. You understand what I'm trying to say? Yeah. Now the logic will be, I will have 180 still. but it will multiply this 0 plus minus 180. It will multiply 1,6667. I don't know if you see what I'm doing. So literally, if I can summarize it easily, you use the first row to fill the two first row here. You use the second row to fill the two at the bottom. Now, it means on this one, I will go minus 180 here times 0 plus 180 times 1,6667. Now I close my matrix. Do you understand what I'm doing, guys?
Can you kindly repeat the second part?
Let me do this. Let's forget about those numbers. Let's say we have 2, 4, 3, 2 multiplied by 1, 2, 4, 5. What I'm saying, I know at the end I'll have a 2 by 2 matrix. What I want you to see, I think is the easiest way of doing it. If I need to fill this row here, I will use these guys here. Now, how do I use them? For the first row, I will have 2 times 1 plus 3 times 2. That makes this one on top. For the bottom, I will have 4 times 1 plus 2 times 2. This makes the second at the bottom. Now, I want to fill the other one. I want to fill the other row on this side. It means this guy should be now my priority of multiplication. Now, how do I do it? I'll have 2 times this 4 plus 3 times 5. Now at the bottom I'll have 4 times 4 plus 2 times 5. Now once I have it here, I can write now my final matrix. In this case will be 2 times 1 plus 6. So 2 times 1 is 2 plus 6. On top you'll be having 8. At the bottom we're going to have 4 times 1, which is 4, plus 2 times 2, 4, which is also 8 by coincidence. 2 times 4, 8. 8 plus 15. 8 plus 15. I think 23 if I'm not mistaken. 16. 16 plus 10. 26. Okay, never mind about this number here. What I want you to get is how we are using this. Do you understand it, Sisi?
Yes, I do. Thank you.
Okay. So what we did at the bottom here is the same logic that we are using on top in our function here. So the logic is the guy. If I want to fill this row, I use this guy. If I want to fill the other row, I use the other guy. So from now it's just a lot of mathematics 1 and 2. In fact, this topic is more mathematics than even mechanical. Let's do. Yes? John, you want to ask something? Mr. Cabello, are you with me?
Yes. I'm here.
Okay, let's take the calculator, my brother. We know already that the 180 will give 0. What is 180? I think the answer is here the same, eh? What is 180 times 1,667? It should be the same answer throughout here.
I think I tell them pendulum.
Yeah, are you talking to me, Aya?
No, sir, I forgot to mute my mic.
Nice. Let me.
To unmute it.
Yeah, you're making someone smile. What is the answer? Yeah. You have a big power. What is 180 times 1,667? Oh, guys, we still have a lot to do, please. But remember, from all these, what we'll be doing is simply
300.
mathematics, matrices. Mr. Kabelo, what's the answer? Calculator Kibukai. It's 300. Yeah, thank you, Sisi. 300. So I guess this one will be minus 300. How do I know? This is 0, this is 0, this is 0, this is 0. So on top here is minus 300. And it's 300 here. What a nice coincidence. So we are not yet done with normalizing. This is just the first part. Remember, the formula of normalizing K. It says that it is m half multiplied by K times m half. So what we did was this one. So what is next? It is this answer that we get here now multiplied by m half. Again, another matrix. So what we have here is 300 minus 300 minus 300, again 300, everything to be multiplied by m half. What is m half? M half is what we got here in the beginning. It is 1,667 there that we got there. Mr. Grabello. I think that's what we got. I think it is 3,6 here. Now again, guys, to normalize this, what will be the final answer of the normalization? It's going to be again, let's use the same logic. I think it will be easier now. We want to fill the first and second row. We will use these two guys. So how do we do that? We'll have 300 times 1,6667 plus minus. So I'm using, basically, as you can see, I'm using this top here and this one to fill the top here. So minus 300 multiplied by 0. I have filled this one. I go to the bottom. On the bottom, I will use the bottom line, but multiply with what? This everything here. That's why you see I will have minus 300 multiplied by 1,667 plus 300 times 0. Now the same thing now, the same rule that I've done there, but now I will use this guy here has priority because I want to fill the other rows there. So it means I'll be having 300 multiplied by 0 plus minus 300 on top multiplied by 1,6667. Again, minus 300 at the bottom multiplied by 0 plus 300 at the bottom multiplied by 1,6667. Ooh. So what do we have here as the normalized matrix, guys? You just need to do 300 multiplied by 1,6667. Remember, this will give 0, this will give 0, this will give 0, this will give 0. Mr. Cabello, what do you have there? Are you with me, guys? Let me hope I'm not talking to myself. 500. I hope if you take a calculator, you have 500. So it means on top here, this one is minus 500. This one is 500. And the other guy here, this one is minus 500. That is if you do calculate. Okay, guys, I can see that the class has been long. I can feel the tiredness from you as well. So I'm gonna stop at the normalization, because what is happening after, it's a bit more of how can I explain, more of math knowledge, is natural, how to find natural frequency. We have to be able to use orthogonal vectors and everything. I just think like it's kinda a lot for tonight. So when we meet next time, we will finish 1.3, 1.4, 1.5 and do another problem. So tomorrow when we meet, we are doing solid, right? According to the timetable. We will start chapter 1 on solid, same time, or I will send the link 10 minutes before. But before I close this one, please, you can speak to me. How was the class? If I was too fast, if I lost you somewhere, if you did not understand me, so that the next time we meet, I improve myself.